Welcome back, welcome back, welcome back. I'm Miss Lisa, and this is my YouTube channel where we talk about everything I want to, science and math related. And today that we're doing physics, we're going to talk about reflection and refraction. This is chapter 17 if you're following along with the class, and there'll be another video that goes over the math, the up close one. Okay. I thought I had more water than that. All right, so what we're talking about is light, and if you didn't watch the videos before, you need to go back and watch those. And the book starts off talking about a rainbow, and they talk about it's a double rainbow, which of course makes me want to go watch the video. Double rainbow. But it talks about how there's more than just the light being bent going on in this rainbow. One of the things you'll notice when you look at a rainbow is the light is brighter under the rainbow than outside of the rainbow. That's interesting. Another thing is, with a double rainbow, the order is reversed. The bottom rainbow will be Roy G. Biv, and the other one will be however you would say it backwards. And part of me wants to figure it out, but it would go the other way. V-I-B-G. See, I told you I wanted to figure it out. So that's interesting too. The thing that you need to know about light is the first thing is it's part of the electromagnetic spectrum. So it's part of Ronald McDonald's Very Ugly Extra Gross. They all travel at the speed of light. They are all light. They are all parts of light. So Ronald is radio waves, McDonald is microwaves, is infrared, very is visible light, and it's just a tiny little sliver of the whole spectrum. So it's really amazing that eyeballs can see light. Makes you think. Very ugly is UV. Extra is X-rays, gross, gamma rays. So that's the whole electromagnetic spectrum, and it all behaves this way. It can all be refracted, it can all be reflected. So just keep that in mind. Yes, we're talking about visible light, but we're also talking about all the light. Now, let's see what else we wanted to say about that. Oh, it all travels at the speed of light, which is 3.8 meters per second, which on Earth is so small, we think of Earth as big, but Earth is so small that that's really instant. So anything that's traveling at that speed of light seems instant on Earth. So if there is a radio station in Atlanta that's sending out its radio signal, it will seem instant that you get it out in West Georgia, and then that get translated into sound waves and come out of your radio. Same thing with a phone call. You could talk to someone in China, and it would be instant that you would be talking to each other because that would be traveling at the speed of light. Now, I think it takes 8 minutes for light from the sun to reach the Earth, but we are a long way away. Now, another thing about the speed of light is the speed of light in a vacuum. So when light is not going through a medium, it slows down. If it's going through air, if it's going through water, it changes to different slower speeds. And that's how light gets bent. But first, we're going to talk about reflection. So if light hits a surface, it bounces off. If a surface is dull and uneven, what makes a surface dull is it's uneven, then the light will be bounced back in a way that doesn't show a reflection. The smoother the surface is, and the reason why is because the light waves go off in all directions. So I can't see myself in this wall right here. But if I had a mirror there, something, or a really shiny piece of metal, a silver spoon, something like that, where it's very, very smooth, then the light will bounce back in the same direction. It'll bounce back together without getting scrambled, and you can see a reflection. So that's our first little thing we need to talk about. The next one is that when things slow down, when light slows down because it's going through a different medium like water, then it's said to be optically dense if it slows it down. Let's see if there's something else. So it said diffused if it spreads out. We're going to talk about the angle of incidence. Let me see if I'm about to talk about something later, and if I will, then I will not talk about it yet. I think I'm going to talk about it now because I don't see it later. It must be around here somewhere. I'll wait and see if we talk about it, if not, I'll talk about it at the end. All right. So there's something called Snell's law that says that a ray of light bends in such a way that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant. So yes, we have to talk about angle of incidence and refraction. Okay, so what this means is, if you have a mirror here, and light's coming in, it comes in at a certain angle. That's called the angle of incidence. It bounces off, it's the angle of reflection. Or reflection is to bounce off, refraction is to bend. So that's the difference in those two terms. If you draw a perpendicular line to the surface, it's called the normal. And yeah, we use the word normal to mean different things in physics, so that's confusing, but it is. And we measure these angles, okay? So Snell's law, we'll go over that math in the next video, but just so you know those terms. Okay, there is a lab you can do on page 352 where you bend light. The thing that works best with any bending light experiment is a laser. If you got a laser pointer, you can see it much better. And you might have to make if you use water, you have to make it cloudy. But if you have a laser pointer, you can mess around with it and learn about how the light bends. Another thing you need to do is get a glass of water and put a straw in it. And notice how when you look from the outside, the straw does not appear straight. It bends. And really, the straw is not bending. You take it back out, it's straight. It's that the light is bending, as is the difference of it going through the air and going through glass and water. Sorry about that, BP. My son is fixing lunch, so I don't want to stop him. So we'll go over those problems. They're not hard and they're fun because you get to use theta, you get to use sine, cosine, things like that on your calculator. You get to do fancy math, and fancy math is always fun math, right? Now let's talk about why the light bends. Let's see. So imagine this. Imagine I've got a little car. I probably have one over there, but I'm not going to go get it. You can imagine. You see a little car, okay? And I'm running it across the floor. I push it, and it's going to hit a rug. But it's not going to hit the rug straight on. It hits it at an angle. So this tire slows down first. This tire out here is still going fast. Can you imagine that? Because of that, when this tire hits first, it's going to whip the car around and it's going to make it turn. Can you see that? And if not, go get a little car, go push it across your floor at a carpet, and you'll see that it doesn't. When if you hit it at an angle, it makes it turn. That's the same thing that happens about why light bends. It's if it hits it at an angle, this beam of light will turn because this part of the beam of light is slowing down faster than this part here, and it turns. Now, and of course, bending light is what causes rainbows. White light is composed of all the colors, but the colors have different wavelengths, and that's why Roy G. Biv is broken up in the visible light. The light has the biggest wavelength with Ronald, and it has the smallest wavelength with gamma. So they get where they're smaller wavelengths. It's all going at the same speed, but different wavelengths, different frequencies, and it causes these different wavelengths make the different colors of the light. So red has a different wavelength than blue, and blue is a shorter wavelength, and that's how it bends into the rainbow. You can see the rainbow there. All right, so we'll go over that math. Talked about all of that. Oh, okay. So you can bend light, and you can bend it more and more and more and more. And eventually you can get it to bend all the way back on itself where it doesn't escape. So if you can imagine, like you've got a light in a fish tank, and then you get to bend and bend more and more and more, and you get just the right angle, then the light will bend all the way back down and not just be bent up in the air. Now, there will be, if it can go into the air, it will, but part of that light will get bent back. So this is the physics idea that fiber optics are based on. Fiber optics is they send information through light that is being bent back into the glass cable that it's made out of. Now, it's not just regular glass, but it is like a glass cable or sort of a plastic-y glass that can be bent, a special material that has a real reflective property. It bends the light back in, and then the light can travel long, long distances through the cable, even if the cable moves, you know, to your house, bringing fiber optic internet to your neighborhood. I don't think we have that. We live too far out in the country, but you city slickers can have that. All right, and so that explains the rainbow. So let's talk a little bit more about rainbows. What bends the light in the rainbow is the raindrops. The white light goes into the raindrop, but because it's curved, it splits the light into the colors, and then the raindrops act together and make the rainbow. And there's more details about this. I'm sure you can go find more YouTube videos if you're interested in a little bit more details about how the rainbow's made. So I want you to look for rainbows this week. I want you to look for glassware that reflects, that makes rainbows, the edges of mirrors, old mirrors that make rainbows, maybe your watch surface, something like that. But I want you to go on a rainbow hunt. Come back and we'll do the math. Like, share, subscribe, and remember, science is great.